Okay, so for today's lecture, first of all, you may realize that we are moving forward to chapter 5. Yeah, chapter 5. We are planning to spend this week to finish the discussion of chapter 5. And then we are going to quickly cover the chapter 8 and 9 as the application of Carnot cycle that will be discussed this week. And then we will come back and take a look at the chapter 6. What would be the useful things in order to prepare us for the discussion of fluids. And then moving forward, you are going to have the mixtures, phase behavior, and their related calculations. So in classical thermal, or the thermal class we are having right now, the discussion would be sort of the following. Are you able to hear me and see the slides?
Yeah.
Okay, thank you. So in general, in classical thermal, we try to take a look at the following thing. We try to understand the pure substance with mixture. Very likely we are interested in gas and liquids. And we may slightly touch on solid, but not too much. We will explain why solid is not that involved in the classical thermal discussion later. And then, of course, while we are working on those fluids, we try to understand what would be the best way to manipulate their phase, their thermal state, so that we can take advantage of the heat and work. So heat and work. That is really the target. We try to get the conversion, or we try to understand how much heat or work needed in order to make a change. And then in between, we need to define those tools, right? So we have those equations. We try to introduce more and more quantities to help us with those calculations. So that is really the general view of what classical thermal discussion. So now if we try to recall, we will discuss quite a few topics. The most recent one, we were trying to understand indeed the heat, if we could find a way to convert the heat calculation as the delta U, if this is the specific heat C sub V, or if this is the steady state flow process, then we try to look at this CP calculation, right? Last time when we were talking about the heat effect, then we try to divide the heat purely using heat to make three possible changes. One is simply working with the pure substance. To change the temperature, right? So there, that would be the specific heat related. Simply change the thermal state. More likely, temperature. The second case would be the phase change. Say vapor to liquid or liquid to solid, then we are going to use the latent heat. And the third case would be the reactions, right? So in order to have the discussion of the reaction, we again define the standard state. We were talking about the heat of formation, heat of reaction, and then temperature effect, which is designing the path for the calculation. So I included a few examples in last lecture, and I hope you guys are reading and trying to understand why those calculations were designed in this way or that way, why we are using this equation instead of the other equations. So this is quite important for this coming exam too. So talking about the exam, I also want to mention that we are still working on the exam 1 grading. And while looking at your submission, I realized that not too many people were having enough time for the problem 3. Which is supposed to be the more interesting or slightly more challenging problem, was 50 points. Of course, I'm not that happy to just look at the information you provided in your submission and try to decide who's going to receive more partial credit. So instead of this, I'm trying to give you 2 more other days, like from today till midnight of tomorrow, so that we can work on problem 3 again and resubmit problem 3 for our grading. How do you like this idea?
Sounds great.
Good.
That's great. Will we get like after class the question 3 again, or is it online?
Well, the problem statement should be still online. I'll email the class. I'll try to make sure you have enough time to work on that problem 3 again.
Perfect.
My plan is to give you until tomorrow midnight to resubmit your solution to problem 3. I open that submission on Canvas again, so that you cannot revise P1, P2, but for problem 3, you're going to have another chance to work it out. All right. So moving forward, we need to take a look at the more interesting stuff on work and heat. So the first question we may have is, well, why we want to understand both work and heat. Why not just stick with one and try to make changes to the system? Because work and heat, essentially, they are achieving the same goal of changing the state of the system, right? So why bother to sometimes work on heat, sometimes work on work? So that is a question of the sort of history, what kind of resources we are having in the past, especially a few hundred years ago. We don't have the mechanical engines, and what we could easily have would be the natural resources. And we realized that we could burn, for example, tree and some other stuff to generate heat, and we use that heat for cooking. And later on, we realized that we can actually use the heat to make some changes, and the resulted change would be also useful. So that is why we started with the invention or the use of the heat, and then we realized that we could actually convert heat into work. Then the question is how much heat we shall take in order to receive a fixed amount of work. This is question 1. The second question is what would be the efficiency of utilizing heat? Can we completely utilizing heat in order to receive the needed work or not? So in order to understand that, we need to have the discussion on the second law of thermal. So before that, let's try to look at those very interesting observations. And again, here, second law of thermal was not really derived mathematically, but it was summarized out of the observations and tested over various examples so far. Until now, we don't have any objection to the signal law of thermal, but that may change or may not. So anyway, so if we look at the first law as I have on this slide, so first law says energy is conserved, but we have no idea what would be the direction, right? If I'm going to have work and heat, what would be the flow? Is it always work and heat into the system, or we are going to have the interchange between work and heat? Nevertheless, we have the following observation from our daily life. One is we could easily transform, as I have over here, we could easily transform work into the change of the system. So those would be the change of the systems. So the feeling is work is really nice. Once we have the work amount, we can completely change and utilize work for system change. But heat is not. We cannot completely convert heat into work or make changes of the system. And normally we are going to have roughly around 40%. We will come back on this value why we roughly have quite low efficiency when we are using heat. And then the second opinion we shall agree on would be heat always flow from a hot to cold body. So when we say always flow, we mean without any help. So here we simply have two objects with different temperature. Then we always realize that the heat flow shall be from the hot object to the cold one. So that was from the observation. And if you think about the other processes, let's try to put it as the initial or state A and state B as the final. So when we are looking at those processes and we try to look at those processes as spontaneously changing, so without any further assistance from outside, once we put, for example, the two fluids together, then we try to leave the system and let the system decide what would be the change or the direction of the change. So we can see that for the case one, when we have two fluids at two different temperature, eventually they are going to have the homogeneous uniform temperature for the two fluids. This shall be the final and stable state. And then if we are going to have the even the same temperature but two different fluids, then when we put them together, we are going to have a quite nice mixture instead of two obvious fluid phases. And the third example would be for the chemical reactants. Normally, we are going to have one dominating reaction direction, right? If I have NO and oxygen, they are going to react at a certain condition to produce the products. And of course, the force will be also quite similar to the example 2, when we are going to have the concentration gradient, in the end, we shall receive the uniform mixture. So that is sort of the natural spontaneous direction. We cannot easily have both A to B or B to A happening spontaneously. So that is a quite interesting observation because, you know, if we just use first law of thermal, the energy conservation, we have no idea whether the change would be A to B or B to A. So that is a hint that using the first law of thermal is not enough to understand the nature. We shall come up with some other ideas to understand the direction of the change. And when we talk about the direction of change, I highlighted some keywords here on slide 4, the last part. So we say we need to have some additional requirement or tool that we can discuss the spontaneous process in the isolated. So that is to exclude other factors we need to worry about once we have defined our system. So that would be spontaneous, no extra support, and that would be the isolated. So we are not going to allow the interchange between the system and the surrounding. And then we try to look at or understand why the nature is evolving always in one direction, not necessarily in the reversible way. Okay. So in order to address on those interesting observations, here comes the statement of the signal law. Okay. And we have multiple statements regarding the signal law. So let's take a look at the three statements, the three most popular statements. So the first statement says no apparatus can operate so that it only affect regarding both system and surrounding to convert heat completely into work. So heat 100% to work is impossible, right? That is the statement of 1. The second is no process is possible which consists solely in transferring heat from one temperature level to a higher one. So that says if I have the T cold or cool to T high, T hot, that direction without any help, that is not possible. So that's not the spontaneous heat flow from cold to hot. The third statement says it is impossible by a cyclic process to convert the heat absorbed by a system completely into work. So cyclic process, so this is the initial of A, try to make a cyclic process coming back to the initial, then we understand that it's not possible to completely convert heat into work. Complete meaning 100%. That is also impossible. So that would be the three statements for signal law of thermal. Let's try to see what would be the very basic understanding from the signal law of thermal. So basically it says no spontaneous heat flow from cold to hot. So pay attention to the spontaneous. For some other cases, if you are willing to assist, then of course we are able to transfer heat from cold to hot, like we are always using the refrigerators, right? So that is the case, but for the refrigerators, we have to use electricity. We have to use the engine to drive the cycle, but there's no spontaneous heat flow from cold to work. And the other is there's no 100% complete conversion from heat to work. So the quick understanding from the second law of thermal is if we could choose, then work, the quality of energy from work is usually better than heat, because otherwise heat we are going to waste when we are going to convert heat to work. We'll come back on this in a little bit. So in the following few slides, I was trying to put together some statements made by the giants of thermodynamics, say Kelvin, Kelvin or Planck. We know the Planck constant, right? Same Planck. So let's try to take a look at what were their statements regarding the signal law of thermal. So here I have this illustration. So if we are going to have the thermal energy reservoir I'll explain what would be the meaning of reservoir. So if I have the endless thermal resource from this reservoir, then we cannot achieve the 100% conversion. So here you can see that we are simply converting heat into work. If I take 100 kilowatts as the heat flow rate, but without any change to the surroundings. On the other end, if I have no heat outlet, I just cannot convert this 100 kilowatt completely to the work rate. Okay, so that is very similar to one of the three statements we discussed. And then we also have the Clausius statement. So that is mainly regarding on temperature. So if you look at this cartoon illustration, if I'm going to get a certain amount of heat from the cold reservoir and without any assistance of the work, so you can see that the net work of the system will be zero, then that process is impossible. You cannot receive 5 kilojoule from the cold reservoir and release that spontaneously to the hot reservoir without any involvement of work. So that is the Clausius, his statement. So now you realize that, well, you can see that for this Clausius statement, for the cartoon illustration, we are going to have some units, right? Some here we are also having some units in order to convert between heat and work. So what was needed in order to have the work heat conversion? So that is why we need to take a look at the so-called heat engine. So heat is for heat. Engine is going to produce or is requiring the work input. So heat engine was really the topic, the central focus of thermal around 1700. So this was the indeed the first practical device to store, to receive some work from thermal energy by burning, for example, coal. Nowadays we are using oil in order to receive the work. And the basic idea of the heat engine is that we are going to obtain the mechanical energy, or in a way work. That we are going to have the thermal engine, and we realize that it is possible to receive some mechanical energy if we are going to allow the heat flow from the high. When we have the high to the hot to cold, then we are going to produce along that process to produce some work. Okay. Then the question is, what would be the relationship between T hot, T cold, and the amount of work? What would be the efficiency? How do we maintain the temperature so that I can have the maximum use of the coal? So I was putting together this steam power plant. We were using the steam table for the first exam, and if you realize in the industry, especially chemical industry, steam is really widely used in all sorts of production lines. So let's try to take a look at what is behind the steam power plant. So here I have this much simplified cartoon illustration. So if we stick with this initial, and we realize that is a cyclic process, recycle on the working fluid. So if we start over here, if we have this liquid water, So we realize that always we try to use a pump to change the sound state of the liquid, right? So that is the first one. And if you think about in terms of work and the heat, that is the work input. So we have to pay the price to pump, to compress liquid water. And we are going to transport that to the boiler. And in the boiler, we are going to again provide the energy to change the temperature and drive the phase transformation. So over there, liquid water will be vaporized to have the steam. And the outlet would be the vapor, steam at high temperature and pressure. And then we are going to have the steam moving into the turbine. And the turbine is a unit to produce the work, as suggested from here. We are going to have the work output, right? And then if you look at the working fluid steam, then we are going to have the exhaust steam. So the temperature and pressure shall be dropped. And then we try to further condense that exhaust steam. So we are going to have the condenser, and then over the condenser, we are going to release the heat from the system. So that is the heat release out of the system. Then we are going to have very likely liquid water. Then we are going to transport the water back to the initial inlet of the pump to drive the cycle. So from that illustration, if we try to define this very simple diagram, we are going to have the work and we are going to have some heat input from this hot reservoir. And then we are going to have the work output. At the same time, we are going to discharge the heat to the cold reservoir. So that would be the 4 units we have to use. And then you may have the question, who demands that we need to use the 4 units? And what is the mechanism behind this loop? So in order to understand that, we need to come back. So that is the model, the initial model of the steam engine. So we already have 4 units over there. So if we think about I think on that slide was just the explanation on the change regarding the 4 different steps. But the thermal efficiency was really determined. If you think about this is the input, right? This is the work output. This is the QH. This is the QC. So if you think about that, and if we try to combine the shaft work as the net work output, okay? So that would be the useful work we are going to have. Then you can see that we are basically having this revised. This is QH, this is QC, that would be the shaft work, needed shaft work, or network output. So if we think about the efficiency, we provided that much of heat, and we are going to receive the needed work. So the efficiency is indeed, as we have over here, the thermal efficiency of that process will be defined by the ratio of shaft work or net work output over the heat input. So here we are using the absolute value because we are going to have positive or negative sign regarding the direction of the energy flow, right? However, we shall be finding this correlation very easily. So from the first law of thermal, then we realize that the absolute value of the shaft work or net work output shall be the difference between QH minus QC, right? So over there, we can see that the thermal efficiency is purely determined by the two reservoirs you are working with. So that is the efficiency definition. And of course, in order to improve the efficiency, we try to minimize the heat release. If we can have the minimize the QC, then the efficiency will be much closer to 100%. So coming back to the previous question, who told us we need to have the 4 units? Well, that is from Nicholas Carnot. So I have one single slide to really briefly introduce him. He's a very interesting fellow, and I would encourage you to Google or to visit Wikipedia page of him and try to understand a little bit of his philosophy over there. So nowadays you can see that we consider him as the father of thermodynamics because really the contribution to the Carnot cycle, the heat engine, and the fundamental designing what would be the maximal efficiency if we are dealing with a certain temperature conditions, what would be the maximum work we can receive. So he's responsible for the at least 3 concepts we are going to have in this class, say Carnot efficiency, Carnot theorem, Carnot heat engine, that will be discussed in today's lecture. And then of course Clausius, Kelvin, they made other significant improvement upon his finding and later introduced one other very important concept of thermal entropy. We'll discuss that next lecture. So the question Carnot was thinking about was simply this one. So he was trying to understand what would be the maximum efficiency if we design the heat engine. And the heat engine is we are going to use heat as input. And then we try to have the work output. So what would be the maximum efficiency? While looking at the design, at his time, we already had the understanding of the signal law of thermal. That is, we cannot have the 100% conversion. So somewhere we are going to waste some heat. We're going to have some heat output. And then we just need to figure out what would be the maximum efficiency regarding the 3 energy forms. So long story short, he designed his so-called Carnot heat engine. And the requirement would be, one is we need to have this reversible. We'll come back a little bit on this reversible statement. And then according to his result, we need to have the 4 steps. So he explained, he designed, he illustrated to us what would be the maximum efficiency for any heat engine. And you can see that nowadays we are still following his design for all sorts of heat engine or any device that we try to use to convert heat into work. So let's jump to his design. So here is the general diagram of the Carnot engine. So let's try to pay some attention to this diagram. So number 1, we have the PV diagram, right? So if we are looking at the PV diagram, then the area under the curve should be the work because work is calculated by PDV. So that is quite convenient to use a PV diagram. Number 2, let's try to pay attention to the direction of the flow. So let's suppose we are walking from A to B, then you can see that this is a clockwise change. So we are moving along this direction. On next slide, we are going to talk about the reversible Carnot cycle, which is not the heat engine, but the refrigerator type of process. Number three, we need to take a look at the requirement of each unit. I hope by now we are happy with those terms, say isothermal and adiabatic. Compression, expansion, simply trying to connect what would be the volume change of the system. So if we try to take a look at the first pass or the first unit, that is related with the pump, right? If we recall the heat engine we just briefly discussed. So over here, the requirement is we need to have this adiabatic. Adiabatic meaning we don't have any heat involved in the process, and we try to compress the liquid. So that is the change from A to B. Then along B, we are going to have the isotherm expansion. Isotherm means the T temperature change would be 0, or temperature is fixed, and we are going to have the expansion, right? So over there, we are going to have the corresponding unit of boiler. Okay. So over there, you can see that we are going to drive the liquid into vapor, having the phase transformation until we are receiving the final state of C. So from C to D, that's another adiabatic isotherm, right? So here, the only difference is now we are going to have the expansion. That is the turbine. Okay, corresponding the turbine. So over there, we are going to have the work produced over this unit. And since this is the adiabatic, make sure you have that hand or provided condition. And now we are here at D after the turbine. We are going to have the exhausted steam. Then we are going to have the condenser, moving the working fluid back to the initial liquid state. And of course, along that process, the temperature is constant. dT would be 0. Very much explained by this. So if we take a look at the other information, we realize that we are going to have the work input. Let's say this is the work input. That is the work output. But like we discussed on the previous slide, we try to combine that two work as the work network. So that network would be from the turbine minus the work needed from the pump. This is regarding the work. And then for the heat, we are going to have the heat flow into the system at this high temperature. So this is the heat into the system. This is the heat outside of the system, right? So then we can have, if we quickly apply this first law of thermal, simply looking at their values, let's say, that would be Q input minus Q output. Okay, that is the answer. That is basically the answer. So Carnot was utilizing the second law of thermal, meaning we have to release, we have to discharge, we have to waste some heat energy in order to produce the work. This is number one. Number two, from his design, we need to include the following 4 units. This is the second point. The third point is he claimed that is the maximum efficiency if you are able to somehow design this process. There's no way you can have a better efficiency regarding heat engine. So we'll come back in a minute to validate his statement of the maximum efficiency. But before that, let's try to take a look at a quick check on the reversible. So it's not the same direction. Now you can see that this is not clockwise. This is moving unclockwise. Yeah. Why? Okay. This is the reversible direction. We are still having the exact same setup of the diagram. We are still having the exact same 4 units. So we always need 4 units moving forward. But depending on the direction, we could have the heat engine or we could have the refrigerator. So now we try to get some heat input from the cold object, and we are going to release the heat in the hot object, right? And we'll come back on that when we discuss the units in chapter 8 and 9. So the first interesting stuff is let's try to look at the current theory, which is his engine is the best engine with the maximum efficiency. So let's try to take a look at those. I enjoy the philosophy involved in the proof. So let's quickly check on how we can prove his statement. And as I put over here, you can also read that statement or the proof procedure from the textbook. So let's try to have a quick check on the proof. So that says if we are going to have the hot reservoir, cold reservoir, and we are using some engine in between, so that we can take the input output and we are going to produce work. So over here, let's try to put Carnot's engine. C stands for Carnot. The Carnot cycle, as shown on this diagram, will absorb heat QH at this hot temperature and will produce that amount of work. And then it's going to reject the heat, that amount of heat at cold temperature. So that is nothing but we just use Carnot's engine to achieve the purpose of converting heat into work. So then we try to have this assumption. Suppose we are going to find another engine, E. So that's a different engine. And this type of engine will exist with more efficiency, with a better efficiency than the Carnot's engine, all right? And that engine is working still in between the same condition, THTC. And in order to achieve a better efficiency, then we need to look at from the efficiency definition, which is work out of Q in or QH, right? So now following that assumption, we try to derive that, well, it's the same amount of work, and this new engine will be a better one, so it's going to require less input in order to achieve this larger efficiency. Well, this is the Carnot's engine heat input. So that is following the assumption. Suppose we are able to design a better engine than Carnot's. then we are going to have this statement. That means the Carnot engine will need a larger input from the hot reservoir. So what we can do right now is if you try to recall, we also mentioned the Carnot engine should be reversible, meaning changing the direction makes no difference to the efficiency or to the thermal calculation. So this is why we come up with this very nice idea. So now we try to combine this beta engine together with Carnot's reversible cycle. So now you can see that we are reversing the direction. We are going to receive the heat input from the cold reservoir. We are going to need some assistance as a work input, and altogether we are going to discharge the heat to the hot reservoir. We need to have the work assistance, otherwise it's a violation of the second law. We cannot automatically transfer heat from the cold to the hot, right? So that is why we need to have this work input. And now the nice part is now if we try to combine that work output from the beta heat engine, and we use that amount of work as the required work input to the Carnot reversible engine. Then we can see that if we are going to design a new system, now we try to look this as a whole system. Nothing special, but the system is composed of two units. One is the heat engine, one is the Carnot reversible engine, right? So now if we try to run the analysis, so that would be the flow in, that would be the flow out of the system. And on the same time, we are going to have another flow into the system and flow outside of the system. And you realize that the work exchange between the heat engine and the Carnot engine, it's happening internally, right? So when we have the system defined as the combination, there is no work input. So there, if we try to take a look at those numerical calculations, so that is the heat output, heat input, output, and input. So if we try to take a look at these two relative value at one end, so if we look at the cold reservoir, so we are going to add the two values together. So that is the one from the reversible Carnot cycle. That is the one as the input into the cold reservoir. And if we just cancel this work, then we are going to receive QH minus QH prime, right? And if we agree with assumption, the new heat engine is better than Carnot, then this input is less than Carnot engine heat flow. So this is why that is a positive one. So the net, meaning there is a net output from the code, okay? And then on the other side, if we try to take a look at this QH minus QH prime, that's again a positive value, meaning QH is into this, QH prime is out of the hot, so their net would be, we are going to have a net heat flow into the hot reservoir. So now you realize there is a problem because using this as my design of the system, there's no work input or output. No work is involved in the system, but with that system, we are able to receive some heat input from the cold reservoir, and we are going to dump the heat to the hot reservoir. That's the obvious violation of the second law of thermal. And we have been doing everything perfectly except for this assumption, right? So this is why we can prove why Carnot cycle is the best one. There's no way we can find a better heat engine working between the hot and cold reservoir. And Carnot, he proved that quite a few hundred years ago. And it's done really beautifully, right? So I think I owe you some explanation. What do we mean by reservoir? Reservoir means we are going to have the endless size or energy storage over there. So if you try to get some heat flow out, you are not going to change the temperature of the reservoir. So the temperature will be maintained always at TH or TC, regardless the amount of heat input or output you are having. Any problem so far? Is anybody having any question? No?
Not really.
Okay, good. I hope you are going to do some reading and try to understand the way he proved the theory. I think this is really nice, and it involves the second law of thermal. It involves a new design of the system, all right? And of course, it involves some numerical calculation over there. So that is the answer. No engine can be more efficient than the reversible Carnot cycle. Okay. So now with this proof, we actually have other very important stuff. So let's say that we just realized that we need to look at the TH, the TC, and when we define the Carnot cycle, we did not have any requirement. What would be the working fluid? Do we have to stick with water, with steam, or we can use, for example, CO2 as a fluid in the Carnot engine? So using the previous proof, we are able to come up with this second statement, which is the Carnot engine does not depend on the working substance. We could pick up any substance we are happy with, and we are able to achieve the same efficiency, as long as this is a Carnot type of engine, reversible, and the engine is composed of the 4 units, as we saw on the previous slide, then the efficiency should be exactly the same. I'm not trying to go over this slide 21 again, but that was basically the very much same idea. We try to prove that using ideal gas and any real liquid, we are going to achieve the same efficiency. You can see that we try to use the statement, say, maybe the liquid will generate a better efficiency, but we are able to prove that assumption is wrong. So eventually we realize that whatever working fluid you are going to use, the Carnot engine will always produce the same and the maximum efficiency working between the 2 reservoirs. Okay. So then the second statement will provide us also a very strong hint, which is, well, there is no need to distinguish what is your working fluid. Then, of course, to us, the most simple case would be ideal gas, right? If you are using ideal gas, we could achieve the same efficiency, then why not? This is the easiest model in thermal, and we should be able to calculate all sorts of properties very easily using PV is RT, right? Work or heat flow, the same type of calculation we had in exam 1. So let's try to take a look at the summary, a short summary of Carnot's theory. So it says for two given heat reservoirs, TH and TC, no engine can have a higher efficiency than a reversible Carnot engine. The efficiency of any real, irreversible, or spontaneous heat engine is always less than the ideal Carnot cycle. The second understanding from his theory will be the efficiencies of all reversible heat engine, meaning Carnot engine, operating between the same two heat reservoirs will be exactly the same. The maximum efficiency, as long as you've identified your interested TH and TC, then the efficiency will be always the same, regardless the working fluid, regardless the path you are going to design, as long as it's reversible Carnot cycle. Okay. The third is also very convenient. We'll see in a minute. The efficiency of a reversible Carnot engine depends only on TH and TC, not on the type of fluid. So there we try to extend the statement that we are going to use ideal gas for the Carnot engine discussions in just a minute. The third would be quite useful to give us some feeling. So normally when we think about all potential working fluid, and I want to add why we are always stick with steam, because it's cheap. You could have all sorts of advanced working fluids if you are having a specialized engine, say for the outer space project. But in our daily life on a much larger scale for the population, then we'd better stick with the easy resources, right? This is why water and steam would be the most convenient one, and we try to stick with the steam. So this leads to the maximum efficiency for the heat engine. So that is why we are having the understanding why the normal efficiency would be around 30 to 50%. This is simply because when we try to use water as a working fluid, then this is the room temperature or the convenient liquid phase of the water. And on the hot TH end, we are able to, of course, increase the temperature, but there we are going to waste lots of work over there to drive the vapor into the superheated vapor, right? So this is why the normal working steam will be between 5 to 600 Kelvin. And then considering the THTC, we're able to estimate what would be the maximum efficiency. Okay, in just a minute. So now let's try to come back again on the Carnot engine. Like I said, I could not read his mind. How many other designs he had tried in order to come up with this perfect solution. So for us, we try to appreciate his result and try to understand what would be involved in his design, not trying to ask, well, you could, but it's hard to carry out the full-length discussion why we started with the adiabatic, why not fixed pressure, isobaric, but we need to have this isothermal expansion and compression, right? So we simply take it, and we also have validated that his design is indeed the best heat engine. Okay. So now if you try to think about the general, let's say general heat engine. We understand the efficiency is defined by the work output, this input, right? So let's try to see what would be this efficiency definition if we apply into kernel. What would be that efficiency? So that is also a fantastic question to ask, and we are actually able to solve this puzzle, because that's simply the calculation. We need to figure out what is the equation for the work, what is the amount of energy for the QH, if we try to stick with this PV diagram. So that is basically coming back to the ideal gas. This is because Carnot's theory states that the working fluid does not matter. So we stick with ideal gas and try to understand the Carnot cycle. What would be the Q and work for each unit? Okay. So that would be the discussion on the following slides. So where do we start? Well, we start with some general equation. The most useful, the first one would be the first law of thermal. So if we quickly revisit, this du would be small amount of heat and the work. So try to manipulate and try to replace this work as the PV function. Try to replace du, which is state function as CV dt. Then very quickly we are having the equation 1. Small amount of heat is CV dt plus PdV. Okay, that is for the general discussion. And now if we try to stick with this individual unit, let's try to revisit this. Now we try to calculate the first part, which is the isothermal expansion from B to C. And we need to figure out what would be the QH, right? So QH is again is CV dt minus plus PdE, like we just described. And that change is coming out of from the initial of B to the final of C. By the way, over here, we realized that in the first exam, many of us were still quite confused. If you try to calculate the change, change is always calculated by final minus initial. So if you think about the problem we had, it's say, if you are calculating delta H, it's always H2 minus H1. I think we saw a few examples. Some of you got confused using H1 minus H2. Then you are going to mess up the sign or the following calculation. So try to pay attention over the change calculation. It's always from initial to final. So final value minus initial would be the change. So if we try to look at what I have over here, then we have the isothermal expansion. It's from the fixed temperature pH, and suppose those B and C, that two conditions are known to us. So we have PB, VB, the pressure, and the volume at condition C. So now you see the convenience of using ideal gas. PV is R, TH is the fixed temperature. So over there, the temperature is fixed, so CV dt would be 0, right? So there, we are going to have this delta Q is du plus PdV. This one would be 0, so simply PdV over there. And P is RT over V. RT over V. Just replace the pressure by the ideal gas equation.
and we are making the change from the initial to the final. So run this integration, you could quickly have, this is the amount of heat input to the Carnot cycle for a step from unit B to C, right? What about the D to A? What is that D to A? D to A is the corresponding sort of reversible to this B to C. So now if we go back, run a quick check, this is D to A. We figured that out. We try to figure out what would be the heat output from the isothermal compression unit. D to A would be exactly the same, just change the initial and final state. Still using the PV over RT. Still, we are doing this at the fixed temperature, but now the fixed temperature is T sub C. We are still using QC. The du would be 0, CV dt would be 0. So over here, we are still using PDV, replacing the pressure by RTC over V, paying attention to the starting and the final conditions, moving from D to A. So there we have this equation, Q. So what's the use of that? Well, at least we are able to replace this year's W work over QH, and W, if we are using the first law of thermal, that would be QH minus QC. QH. So now you can see that we are achieving a very nice objective over here. We are able to replace the work terms in the general definition of a heat engine by the state parameters, right? We're able to converting QH over QC by the temperature we could measure, by the volume ratio we could also measure. So this is the general heat engine. And if we are using following Carnot engine, then we are able to simplify this. It does not look like we are simplifying, but we'll see after the following two slides. At the same time, now if we try to look at the other two steps where we are having the adiabatic compression and expansion on both sides. So over there, since this is adiabatic, this dq is 0. So now we are trying to deal with this du would be simply the work equation, right? So this is why CV dt is minus PdV. And again, we are using the ideal gas equation, RT over V. We try to rearrange, we try to put the temperature terms together. We have dt, we have T. So I'm going to move the temperature over there and put the volume terms on the other side. So this is why we are happy with the equation 5 over here. So now we are going to use the equation 5 on both units for the adiabatic process. One is compression from A to B. The other is coming out of C to D, right? This expansion. So simply running the integration, we are going to have this term. The same would be that term. So moving from TC, so that is TC to TH. That is A to B. Now, if we are looking at this C to D, we are having this TH coming back to TC. So that is the equation we derive for A to B process. For C to D, very similarly, we are going to have this equation is again to this log ratio involving the two volume. So now if you compare, and I leave that to you, now if you try to look at the two terms, they shall be identical on the right side, only missing one sign. So this is why if we are looking at the VA over VB, VD over VC, let me try to highlight. So the on the right hand side they are identical, on the left identical, on the right shall be also identical. So this is why we come up with that equation. Now if you recall the previous equation we just derived for the isothermal process, B to C, D to A, then we realize that we are having this very nice equation. So if we go back a minute to equation 4, what we just did was to confirm this is actually equals 1, right? So over there we can further simplify for Carnot cycle QH over QC is just the TH over TC. Okay? So that is the charming of Carnot cycle. So there we are going to have this equation for Carnot cycle. Whether it's the standard Carnot heat engine or reversible Carnot engine, the refrigerating process, we are using this as the efficiency calculation. So if you think about 1 minus TC over TH, and what we just talked about, this is roughly around 300 Kelvin, very convenient for liquid water. This is roughly 500 to 600 Kelvin, and that is the limitation we have to accept. Using steam, using liquid water, then the best engine, the efficiency is around 30 to 50. All right, so I'm going to stop here. The following slides would be just a repeat of what we talked about, and you can run a quick check on the calculation. So before we leave, any question for this lecture? I was basically building up this lecture on the previous calculation, okay, of the work of the heat for the ideal gas. So if you are not very happy with the slides on, for example, this slide or any of those slides regarding the Carnot cycle, you should visit the previous lecture on ideal gas equation and related work and heat calculation.
Dr. Paul?
Yep.
Will there be some sort of other curve for the test, because some of us did question 3 instead of spending a lot of time on 2 and 1 because it was worth so much points? But now you're letting us redo 3, but some of us already did 3 on the exam.
That's a good question. Well, I have to discuss with each individual if this is a concern to you. Otherwise, we have to take the whole exam, right? You could easily argue that I was working on P2 and P3.
Yeah.
So right now the decision is only for P3.
Okay. Thank you.
Yep. All right, if no other question, then we'll see each other on this Thursday.
I also did most of question 3, but did not do all of question 2.
Well, you email me and I'll check your paper to see what was the status. Right now, I cannot promise that we are going to retake all the 3 problems, but only problem 3. Okay.
All right, thank you.